Okay, brief review of Legendre transform. Okay, that's a good idea. So did you guys get to the tutorial part of the Legendre transform, or let me see. Let me bring up the tutorial that will help me. All right. So the idea of a Legendre transform is that, of course, in stat mech, we are doing it for like two functions of more than one variable, but the idea is valid for functions of one variable. Okay, so the idea is something like this. Suppose you have a function. So we draw this function. F is the dependent variable, and the x x is the independent variable. So, and suppose we have some function, something like this. Okay, and so the idea is that if we now take the derivative of this function, and let's call that u. So df by dx, then can we think of the function f as a function of u? And why are we interested in this? Well, for many reasons, because it has applications in physics. For example, we know that when we are looking at momentum, we are looking at the time derivative, right? So we can sometimes, so that now we know that when we take the derivative of a function, some information are lost, right? So for example, we can always add to f a constant, and then the derivative of f with respect to x will be the same as the derivative of f prime with respect to x. So we know that this is actually, if you are given the value of f, for a value of u, then it's not going to give us a unique. It's not going to. We won't be able to reconstruct f as a unique, uniquely from it. So for this particular example, let's just look at what the function of f may look like as a function of u. So basically, what we can do is that we can say, okay, let's just take a value of u, so and then this is f, and if I plot it, if I look at this function, the slope here is very small, and the slope here is very large. So heuristically, it's going to be given by something like this, right? This is the example I gave. All right, so now the idea is that what if I want to reconstruct a function which has this sort of profile of the function as a function of the slope, what are the functions we can get? Well, we can get many functions. So as I said before, for example, we can get the original function, but we can also get stuff like that. So to get the to be able to reconstruct the original function, we need another information, if I give you the slope, I also need to give you the intercept, right? So now if I give you the slope, you can draw like a straight line like this with the same slope, but that straight line can be anywhere, right? Because all these straight lines will have the same slope, right? So if I give you the correct intercept, then that that's the straight line that you're looking for is going to touch your function at some point. Now you don't know where this point is. You just know the slope, that is this is the slope, and you know the intercept. You know where it intercepted the y-axis, or in this case, I'm calling it the f-axis. But you don't know where this line is actually, making contact with the original function, because you don't know what the original function is, right? Is that clear?
Yes, sir.
Yes, sir.
Now, if I give you, now you take the slope of this and then you change the slope a little bit. You increase the slope a little bit. Then you get another line. Say, let me just draw that line. So that line has a little bit more of a slope, right? This has more slope. And it could be any of these lines, right? But if I give you the intercept of that line as well, then you know that that is going to be, it's going to touch this curve, at a point a bit higher than the previous line, right? So if I give you all these, so if I give you for every value of u, right? If I give you the intercept as a function of u, then what you will get is that you will be able to reconstruct our original function as the envelope function for all the tangent lines. Okay? So you have, you have an infinite number of lines, the slope of each of which is given by u, and the intercept of each of which is given by g. But if you can draw all of these things, there will be like an envelope function, right, for all these things, for all these, and that envelope function is the original function f of x. And then basically you can just go ahead and verify that if your original function is f of x, and that is equal to, well, the slope at the point x, and I think it's minus, yeah. Sorry, what am I saying? That's not what. Yeah. So if I think it's f of x is x times u and minus g of, if this is it, then what do we have is that let me see if I'm doing this right. Then d of f by d of x is u, right? Which is what I wanted. And I think this is probably a plus sign, because it's y is equal to mx plus c, right? So yeah, that should be. And then g of u is going to be f of x minus x of u. Okay, so this gives you the intercept of the of each of these lines of the slope u in the f-axis, and this is essentially the Legendre transformation, right? So this has, so this function has all the information that you need as a function of u to be able to reconstruct the original function, because whatever you choose, you're going to get the intercept. Okay, so this is essentially what the Legendre transformation means, is that you can reconstruct a function if I give you all the tangent lines to it, all the slopes of all the tangent lines, plus where these tangent lines intersect the y-axis. Okay, is that barely alive? Is that the technical bits you can figure out from the tutorial, and that's really the technical bit is very easy, right? I mean, it's just this like, how do you find the slope from this function? Well, all you do is you say what value of x, you just take the, and then you get minus x, right? And so that will give you that'll basically give you the value of x for a particular value of f of x, right? So
sir,
yeah.
How I forgot my question.
I mean, so let me recap. Okay, let me recap that you have some function f of x, and but I don't tell you what this function is. I give you I give you g of u, where g of u is the function of intercepts of the tangent lines, right? Then you can reconstruct the original function by just saying that, well, this original function is the x times the tangent plus the intercept, right? This is the equation for if I fix the value of if I what am I trying to say is, for a fixed value of u, right? This is the equation for a line, right?
Yes, sir.
So that means
I remember my question. Isn't g a function of u and x both? How is it not a function of x?
Is g? I mean, it is in a sense a function of x, but that's is g a function of so if I fix a value of u, then you can see that g does not change. It's we are interpreting this as a straight line, right? So G
Yes.
of U in that case is fixed, right?
Yeah, I was referring to where we defined G of U, where it was f of x minus xu.
I mean, in a sense it is, because G of U is a function of U and U is a function of X, right?
Yeah.
So in that sense it is, yeah. Okay, so in that sense it is a function, but so this is more of an interpretation that we are making, right?
Were we trying to remove the X dependence, or was that not the goal?
Yes, we are trying to remove the X dependence, right? Because, to reconstruct f of X, we just need U as an independent variable. We don't need to know the X dependence of U, right? And we only need the G as a function of U. We don't need the X dependence here. So you treat this as an independent variable, right? So you're not thinking of it as a function of X. So you don't need to know how U was derived from f of X by doing this, right? You just think of, U takes value in the real line. Okay? That's all you need.
I see. Okay.
Maybe in some finite subset of the real line, but whatever. And then you need G of U as a function of U. If I give it these, I mean, this is given. This is like trivial. All you need for this is just the limit. This is the thing that I need to give you, but I need to give you this as a function of U. And then you can reconstruct what this thing is, right? So in that sense, G is not a function of U. Sorry, it's not a function of X, right? All right?
Yes.
Okay, so basically the Legendre, this is the, because you'll be using Legendre transformation a lot in your life if you're a physicist, if you end up, going to physics, but nobody teaches the geometrical interpretation of Legendre transformation, especially, so this is, so yeah, it's good to know, not that it becomes that you'll be using this particular geometric transformation a lot in your life, but if you didn't know about it, you will always have a little bit of a nagging feeling at the back of your mind that, we always use this Legendre transformation, but it's like a black box that we use. What's inside the black box? So that's the point of this tutorial, is that you now know what's inside this black box.